Hello everyone. The topic for our final year project is DC motor speed control. The group members are Sanket Tikade, Rohit Matre, Bhavish Shetty and myself Vinish Shetty. Next slide. What is a DC motor? Before explaining to you what is a DC motor, I would like to explain what is an electric motor. Electric motors are devices that convert electrical energy into mechanical energy, usually in the form of rotational motion. In simple terms, they are devices that use electric power to generate motive power. What is the principle of operation of an electric motor? Do you remember being taught Fleming's left hand rule at school? Electric motors are an application of this rule with the force generated by electric current flowing through a coil in the presence of a magnetic field causing the motor shaft to rotate. Now, what is a DC motor? A DC motor or direct current motor is an electrical machine that transforms electrical energy into mechanical energy by creating a magnetic field that is powered by direct current. When a DC motor is powered, a magnetic field is created in its stator. The field attracts and repels magnets on the rotor. This causes the rotor to rotate. To keep the rotor continually rotating, the commutator that is attached to brushes connected to the power source supply current to the motor wire windings. One of the reasons DC motors are preferred over other type of motors is their ability to control their speed, which is a necessity for industrial machinery. What are the speed control methods of DC motor? First, speed control of shunt motor, flux control method. Speed of a DC motor is inversely proportional to the flux per pole. Thus, by decreasing the flux, speed can be increased and vice versa. To control the flux, a rheostat is added in series with the field winding. Adding more resistance in series with the field winding will increase the speed as it decreases the flux. In shunt motors, as field current is relatively very small, ISR to or loss is small. Therefore, this method is quite efficient. Though speed can be increased above the rated value by adding flux with this method, it puts a limit to maximum speed as weakening of field flux beyond a limit will adversely affect the commutation. Second method is armature control method. Speed of a DC motor is directly proportional to the back EMF EB, and EB is given by the equation V minus IaRa, where Ia is armature current and Ra is armature resistance. V is the supply voltage. That means when supply voltage V and the armature resistance Ra are kept constant, then the speed is directly proportional to armature current Ia. Thus, if we add resistance in series with the armature, Ia decreases and hence the speed also decreases. Greater the resistance in series with the armature, greater the decrease in speed. Now, what are the applications of DC motors? The main applications of the three types of direct current motors are for series motors. The series DC motors are used where high starting torque is required and variations in speed are possible. For example, the series motors are used in the traction system, cranes, air compressors, vacuum cleaner, sewing machine, etc. Shunt motors. The shunt motors are used where constant speed is required and starting conditions are not severe. The various applications of DC shunt motor are in lathe machines, centrifugal pumps, fans, blowers, conveyors, lifts, spinning machines, etc. Compound motors. The compound motors are used where higher starting torque and fairly constant speed is required. The examples of usage of compound motors are in pressers, conveyors, elevators, rolling mills, heavy planners, etc. Now the next slide would be explained by Rohit.
So, the simulation part of the DC motor speed control, our group have tried with in two ways. Firstly, with the LabVIEW part, and the second is the MATLAB or Simulink models. So, coming towards the LabVIEW, what we have done is that we have made a simple graphical user interface for DC motor speed control. So, as we all can see in the front panel, this is the front panel. There are five different buttons on the GUI for clock or clockwise rotation, stopping the stepper motor, accelerating and re-accelerating the motor. With the help of the buttons GUI created in LabVIEW, In means we have used the LED buttons. Means what the process we want to continue for it. We can do by clicking on it. So this can be done by connecting the serial communications between Arduino and LabVIEW. So next slide, we can see the block diagram for what we get the front panel in, as in the previous slide. So in block diagram, we used a Visa configure serial port. Means this block will help us to open the serial port before executing the algorithm. And we used a Visa close block while loop for continuing the loop. Flat sequences, as we can see the flat sequences that which added the frame after frame. Visa write blocks which write the buffer contains data to be written to device. And the main part, that is case structure, in which we use all local variables and selected as command box a box and given input terminal constant as C. Means it is used, as I said, we used for clockwise rotation, similarly done for counterclockwise accelerating. Here we can see some letters like we have done C to for rotating clockwise, A for counterclockwise, H to rotate the motor at higher speed or accelerating the motor, L for rotating the motor at lower speed or deaccelerating the motor. And last, that's S for the stop button, which is shown in round LEDs, which was shown in round LEDs in front panel. And at the end, after sending all the commands, we must need to close the serial port so that unnecessary exchange of commands could be avoided. So in the last frame, we can see there is a clear all commands in the third frame. So that case structure, that is means it will act like sending no commands to serial port, which will be helpful in closing the serial port. Similarly, another case structure to start the program when we want and stop to terminate the program. So this is what we can use this LabVIEW simulations in various applications of various types of DC motors, as before it was explained by my friend. So further MATLAB Simulink models will be explained by Sanket.
Uh, so now I'll explain the MATLAB Simulink model. This model is this model is through PID controller. We are using a PID controller for the speed control of the DC motor. So we took first of all we took a DC voltage source to give the field system supply, and for a reference signal we have used a constant, and we have all connected to our DC machine, whose model is 5 HP 240 volt, 1750 RPM, and field voltage is 150 volt. Now the value of DC source input is 150 voltage. Now we have connected a control voltage source to to the DC machine, uh, and then the control volt as you can see, the control voltage source is getting an input from the PID control, uh, which is indirectly controlling the voltage of voltage given input voltage to the DC machine, indirectly changing the speed of the machine. So now the control voltage source block is connected to the armature of the DC motor. Uh, we took constant signal and connected it to the comparator and to the input of the PID controller. Now we have connected the bus selector to the DC motor, and as the value of the speed is in radians per second, we used gain to convert it to RPM, and then we have connected the gain to the comparator as a feedback. The value of gain is 30 by pi to convert the radians per second to RPM. Now we use scope here as to see the output of the simulation. We used mux to connect the two input signals, that is the reference speed and the actual speed to the scope. So both of the signal will be plotted in the same scope. and we have used a Power GUI. Now the output of this particular simulation is, you can see it right over here. But as you can see, there is a very big steady state error. So to decrease it, we tuned the PID controller by changing the value of Ka and Ki in the PID such that the steady state error is comes out minimum. So the output is comes like this. So as you can see, in 0.2 seconds, the actual reading is getting 1675 RPM. Now Bhavit will explain the next MATLAB simulation.
Hello, this Simulink model is of a speed control loop of a chopper-fed DC motor. The various blocks in the Simulink model shown are chopper-fed DC motor, thyristor, constant value block, add, gain, diode, etc. In this model, there are various blocks that form a group signifying a certain function. The thyristor, diode, GTO, inductor, voltage source form a chopper. Chopper is a static power electronic device. It acts as a high-speed on-off switch that connects or disconnects the load from the DC source, which creates a chopped DC voltage at the load terminal. Chopper drives are widely used in speed control of DC motors and can achieve speed ranges above or below the rated speed of the motor. The two gains, along with the integrator and the add block, form the speed controller. The DC machine block implements a wound field or permanent magnet DC machine. For the wound field DC machine, access is provided to the field terminals F plus and F minus so that the machine model can be used as a shunt connected or a series connected DC motor. The torque applied to the shaft is provided at the Simulink input TL, which is the torque load. The time scope shows the output, that is the speed of the DC machine. Next slide. It shows the speed of the DC machine and also the electric torque. It is visible that the speed of the DC motor approaches the desired speed after a certain time period. This is the time period during which the corrective action takes place and desired speed is attained. Thank you for watching this video.